We have been doing Lagrange interpolating polynomials, and we're going to do one more example today. Let's say in March, you acquired 9 gerbils. And gerbils reproduce rather fast. So in April, you had 16 of them. I don't know if they reproduce this fast. No, they don't. In September, you had 510 gerbils. October, you had 980. And December, you had 4,320 gerbils. So basically everyone's getting a gerbil for Christmas. So we're going to assume you counted on the first of the month. If you're given a set of data and you want to make nodes out of it so that you can fit a function to it, you have to assign some x values. And for a small set of data like this, interpolating polynomials can be a bit weird just because they're so wiggly, so it's not going to model your data perfectly. For a larger set of data, an interpolating polynomial is definitely better, but obviously we don't want to do a large example out by hand. So if we're given something like this, we have to assign x values. So what I'm going to do is just have like, March be assigned to 3, just because it's the 3rd month of the year. So March will be 3/9. April will be assigned to 4. So 4 and 16. May, not May. We don't have May, we have September. Will be assigned 9. So we could have 9, 5, 10. October is 10. So that's 10, 980. And December is 12. It's the 12th month, of course. So 12, 4, 3, 2, 0. So yeah, if you have a set of data like this, whether it's measurements taken monthly or annually or whatever, you will have to assign the x values. Realistically, a lot of these techniques moving forward are kind of meant to be on a discrete set of data. So like if you're doing, some sort of measurements over time for maybe not gerbils, like temperature or measurements of like the pH levels of a lake or populations or whatever. A lot of our numerical methods are kind of built to work on a discrete set of data like that for the purpose of engineering and science. If you have months like this, you could give them a natural numbering where March is mapped to 3. If you had something like years, you would probably just map the first year to 0 and then go from there. Every subsequent year would be +1 or something. You have to make decisions sometimes about your x values is really the gist of what I'm trying to say. And now we are going to go ahead and find the Lagrange interpolating polynomial, though it's kind of a long example, so I'll just tell you the solutions in certain cases. Here's a reminder of our formula up at the top here. So remember we have L and K, and on the top that's a product of x minus xi, where we skip the term x minus xk. And on the bottom, it's xk minus xi. No, xk minus xi, where we again skip the term xk minus xk. So first we have to figure out n if we're not told directly what n is. And n is going to be one less than the number of nodes we have. We can also think about, if this is the 0th, if we need to count, this is the first node, this is the second node, this is our third node, and this is our fourth node, then n is 4. So if you count your nodes up starting at 0, then n is going to be where you end there. So that means our L's, our polynomials, are going to be L4 whatever. So L4 0 to start. On the top we have, well, we skip x minus x0, so we do x minus x1, x minus x2, x minus x3, x minus x4, and on the bottom, xk minus, oh, not k, sorry. I mean, it is xk, but we know in this case that k is 0. x0 minus x1, x0 minus x2, x0 minus x3, and x0 minus x4. So these polynomials are the most computationally heavy part of doing Lagrange interpolating polynomials. So just another tip, if you're given a data set and you have to make a choice about what the x values are, you don't want to pick big x values. So here it's fine because like I did March equals 3, April equals 4, and so on. So we have smaller x values. We have x minus 4, x2 is 9, x3 is 10, and x4 is 12. And then on the bottom, 3 minus 4, 3 minus 9, 3 minus 10, 3 minus 12. On the top, we have this polynomial that we would need to multiply out. So for this numerator, I ended up with x to the 4th minus 35x cubed plus 442 x squared minus 2352x plus 4320. Oh, that's bizarre. Okay. It's just a sheer coincidence that the 4320 happens to also correspond with the number of gerbils that I have in December. There's no relationship between those. It's sheer coincidence. And then on the bottom, we have 3 minus 4. Well, on the bottom, I look at this and the first thing I think is, okay, I'm going to just have 4 negative numbers. So obviously, if I'm multiplying 4 negative numbers, it's going to become positive. So instead of writing down 3 minus 4 is -1 and so on, I'm just going to ignore the negatives because I know the whole thing will become positive. So we have 1 times 6 times 7 times 9. L40 equals the denominator of this becomes 378. So let's go ahead and compute L41 and then I'll fill in and tell you the other ones. So L41, now in this numerator we skip x minus x1, so we have x minus x0, x minus x2, x minus x3, x minus x4, x1 minus x0, x1 minus x2, x1 minus x3, x1 minus x4. So x0 was 3, So x2 is 9, x3 was 10, and x4 was 12, is 12. And then x1 is 4. So we have 4 minus 3. I am not writing out 4 minus 3. I'm just writing out what the end result is. 4 minus 3 is 1. And again, I'm going to do the same thing as last time where I just say, okay, I know the next 3 numbers are all going to be negative. So 3 negatives will make a negative. And instead of writing out all those negatives, I'm just going to stick a negative in front and then just figure out those numbers like in their absolute value. So x minus 9, or sorry, 4 minus 9 is negative 5. 4 minus 10 is negative 6. And 4 minus 12 is negative 8. So just stick the negative in front of all of that. And what we end up with for L41 is x to the 4th minus 34x cubed plus 411x squared minus 2034x plus 3240 over negative 240. So that's L41. And I have also computed L42, 43, and 44. P4 of x, which is y0, L40 plus y1, L41 plus y2, L42 plus y3, L43 plus y4, L44. So P4 of x ends up being, so the y values, and so I'll just tell you the other L's. The y values, again, come from, this other column here. So 9, 16, 5, 10, 9, 80, 4, 3, 20. So we only use the y values when we're computing the final polynomial. We don't use it to find the L's. So this gives us 9 times L40 plus 16 times L41. And I'm just going to flip back and forth. 510, 980, 4320. 510, 980, 4320. I'm just doing this so I don't have to go up and down. 510 L42, 980 L43, and 4320 L44. Okay, what this ugly in between step is going to look like is 9 times. And then we found L40 plus 16 times L41, which we also computed. $510 times plus 980 times plus 4320 times